today our discussion is about definite integral. Last discussion, we tackled the concept of indefinite integral, which is defined as the set of all antiderivatives. Okay, then we always put C to represent all the constants to be added in an antiderivative, which means that whatever the value of constant C that is added in the function big F, which is the antiderivative, the function produces the same derivative. So before moving on to the discussion of the definition of definite integral, we will discuss first the parts of definite integral. So here are the parts of the definite integral, although some of these symbols or notations, we know this already when we tackled indefinite integral. Just like this symbol, this is the integral symbol or integral sign. Now, in here, in definite integral, we have this letter A and B. Letter A here, this is what we call the lower limit of integration, and B is the upper limit of integration, and this f of x is the integrand, which is the function given, and x is the variable of integration. We also note that A and B can be any real number. Now, we read this one as the integral of f of x dx evaluated from A to B, or simply the integral of f from A to B. Okay, so what do we really mean by definite integral? So, again, we recall that indefinite has no limit, right? That's why the result is always a function with constant C. Here, from the word itself, definite, it has a definite value or the result, which is always constant, because the antiderivative, after solving it, it is being evaluated from A to B. So to relate that one, to understand more on what is really definite integral, we have here its geometric interpretation. Now, suppose we want to know the area, okay, bounded above by this curve. Let's say y is equal to f of x, and bounded below by the x-axis, and also bounded by the lines x is equal to a and x is equal to b. Now, how to compute this area since the shape is irregular? Unlike the concept of areas that we learned in algebra, right? We are already given the formula like the area of a rectangle, area of a circle, a triangle, and many more. But how about this? So to answer this problem, we have here another illustration. Suppose we want to know the area of this region bounded by this curve, and also the x-axis, and also the lines x is equal to 0 and x is equal to 1. How to compute this area? Now here we use the concept of Riemann's sum, which is actually a kind of approximation by partitioning, okay, we partition this region into shapes, and in this case, we partition into rectangles, right? Then the concept is by partitioning the region into sub-intervals or intervals, we form rectangles, and we know that it is easier to compute the area of rectangle, right? Since what we need is the width and the height, then we multiply it, then we have the area of this rectangle. But what have you noticed in this illustration? We notice that as we increase the number of rectangles to infinity, okay, and we sum all the areas of this rectangle, and that is what we mean by Riemann's sum, then it will approximate this area, okay? Though in this case, we have seen that there are still errors in this case. Now, so what is definite integral? Here, the definite integral is mainly interpreted as the area of this curve. Okay, so to translate all our descriptions based on our observations of the partitions by the use of rectangles in this example, we have now the definition of the definite integral. So the definite integral from A to B is given by this. This is integral of f of x dx evaluated from A to B is the number to which all Riemann sums tend as the number of rectangles approaches infinity, and as the width of all rectangles tend to 0. And this is given by this formula. So we have here the definition: integral of f of x dx from a to b is equal to the limit of the summation of f of c sub I times delta x sub I from I is equal to 1 raised to n as n approaches infinity. We have to take note, n here is the number of intervals, and f of c sub I is actually the height of n rectangles, and delta x sub I is the width of the ith rectangle, and c sub I is the x coordinate of the point where the ith rectangle touches f of x sub I. Notice that this summation here is actually the formula for the Riemann sum. And by putting limit of this Riemann sum, it makes the definition of the definite integral. So getting the limit of this summation becomes the definition of the definite integral. So we have here the first fundamental theorem of calculus. This is very, very important if we are asked to evaluate the definite integral. So what does it mean? So the fundamental theorem of calculus states that if we are given a function which is continuous at every point in the closed interval a and b, and f, which is the antiderivative of f on the closed interval a and b, then this equation holds, meaning the definite integral of f of x dx evaluated from a to b is equal to big F of b minus big F of a. Now again, what is big F? Is the antiderivative. This means that this expression is equivalent to or is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So we have here illustrations. We have here illustrations in or examples to clearly understand this fundamental theorem of calculus, or to apply this fundamental theorem of calculus. So first example, find the definite or evaluate the definite integral of 5x dx evaluated from 1 to 5. So all we have to do is to find the antiderivative first. So the antiderivative of that is 5x squared over 2. Then we evaluate this one from 1 to 5. Applying the fundamental theorem of calculus, all we have to do is substitute the upper limit, which is 5, in this antiderivative. So 5 times 5 squared over 2 minus 5 of 1 squared over 2. Then simplify. We have this 125 over 2 minus 5 over 2, which is 120 over 2, which is equal to 60. And it is very clear that the answer of the definite integral is a value or is a real number. That's why it is called definite. Next example, find the integral of sine x dx evaluated from pi over 6 to 2 pi over 3. So what is the antiderivative of this? It's equal to negative cosine x, then evaluated from pi over 6 to 2 pi over 3. So this is equal to negative cosine of 2 pi over 3, which is the upper limit, minus, because that's the definition of the fundamental theorem of calculus, minus the antiderivative of the lower limit. Now, the lower limit is pi over 6. So, to simplify that one, we have negative cosine of 2 pi over 3. The value is negative 1/2, minus cosine of pi over 6. This is equal to square root of 3 over 2, and there is negative here, so we have negative square root of 3 over 2. Then this one, negative times negative 1/2, this becomes 1/2 plus square root of 3 over 2, which is equal to 0.866. So that's the definite integral. Now, next example. So we have the integral of x squared plus 3x minus 2 dx evaluated from 3 to 4. So again, compute the antiderivative. The antiderivative is x cubed over 3 plus 3x squared over 2 minus 2x. Then evaluate that one from 3 to 4. So simply substitute the upper limit first in this antiderivative. So that is 4 cubed over 3 plus 3 times 4 squared over 2 minus 2 times 4 minus 3 cube over 3 plus 3 times 3 raised to 2 over 2 minus 2 times 3. Simplifying that one, we have 37.33 minus 16.5 is equal to 20.3. Now, another example, we have integral of 1 over x raised to 6 over 5 dx, evaluated from 1 to 32. So, again, how to get the antiderivative of this? It's easier to compute this one by what? Converting this or by rewriting this expression into power. So x raised to negative 6 over 5 is just equal to this. Okay, then dx. And applying the formula for finding the antiderivative, if we have x raised to n, what are we going to do? Simply, we add 1. So this becomes x raised to negative 6 over 5 plus 5 over 5 is negative 1 over 5 over negative 1 over 5. Then this can be simplified into negative 5 because this, all we have to do is to, since the exponent is negative 1 over 5, so this can be written here in the denominator, and since negative 1/5, so this can be written as negative 5. So by finding the reciprocal of negative 1 over 5, which is negative 5. So simplifying this, we have, and evaluating from 1 to 32, so negative 5 over x raised to 32. No, negative 5 over 32 raised to 1 over 5, which is fifth root of 32, which is 2, minus 5 over 1 raised to 1 over 5, or the fifth root of 1, which is 1. Then we simplify this one. This is negative 5 over 2 plus 5 over 1, which is equal to 2.5. Okay, so these are examples of finding the definite integral by applying the first fundamental theorem of calculus. So thank you so much. Hope that you learned from this video, and don't forget to share the learning that you've got from this video. Thank you once again, and God bless.